I will begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for these students in this class. Just ask you to bless our work today. Help us understand a little bit more about differential equations together, Lord. In your name I pray, Lord Jesus. Amen. So today I want to talk to you guys about the problem of finding integral curves aka flow lines of a vector field. All right. So basically the idea here is we want to find, for a given vector field, you know, F is a vector field, right? We want to find a path like T maps to R of T, all right, such that F at R of T is equal to dr dt. So what this would mean is that the tangent vector field to the curve would match the vector field at each point of attachment. So like if my vector field, if my path looked like this, or if my path looked like that, or if my path looked like that, then if those are integral curves to a vector field, the vector field, you know, looks something like this. So the question is, how do you find integral curves for a given vector field, right? How do you do that? Apparently, you have to solve this equation right here, right? But that is a differential equation. Now, at the moment, we only have the technology to really solve this problem in 2 dimensions. All right? So let's talk about the 2-dimensional problem. So in that case, we can generically speak about a vector field having like x component p and y component q, right? Like pq. And if you think then about the path you're looking for having components x and y, which we don't know, then what you're trying to solve when you look at f of r of t equals to dr dt, well, what does that mean? That means that you've got p, q equal to, well, dx dt, dy dt, you see? If you'll forgive me, I'm not expressing the fact that the p and q functions must be evaluated at, you know, x of t, y of t, both of them, right? So, hey, this, how can a vector equation be true? It's true if and only if both of the scalar component equations are true, right? So we literally need dx dt equals to p and dy dt is equal to q. Now, we haven't solved problems like that yet in here, really, right? Because that's actually a system of differential equations, right? You have x and y are dependent variables. T is the independent variable. Can we solve a system of differential equations like that? I think we can. Let me show you one we can. So like example 1, we might have f of x comma y equal to, say, x squared, y squared. So if that's the vector field I'm up against, to find the integral curves, I have to solve dx dt equals to x squared and dy dt equals to y squared, right? But we can solve these, right? Because while this is a system of differential equations, they're not intertwined, right? I mean, there's no intertwining of x and y here. You can solve each one of them on their lonesome. Separation of variables, right? You got like dx over x squared equals to dt, and dy over y squared equals to dt. And so lo and behold, we get minus 1 over x is equal to t plus c1.
Construction class.
Is there a classroom? I thought that's an exterior wall. That's weird. Where's that coming from? Anyway. Well, hopefully that doesn't continue. Minus y is equal to t plus c2, right? So we get x is equal to like minus 1 over t plus c1, and y is equal to minus 1 over t plus c2, right? In other words, if you'll allow me to continue this example over here, we found the path r of t is equal to minus 1 over, oh, it's professional. Let's see here, minus 1 over t plus c1 and minus 1 over t plus c2. There you go. That is a parameterization of the integral curve to this vector field, right? There's some really peculiar things about these solutions. Do you notice, like, what's the domain? Notice that, like, if you had the situation where, like, C1 was negative and C2 was negative, then this solution blows up once you get from, like, time 0 all the way over to, like, time C1. Well, minus C1, right? If C1 was, like, minus 3, when you got to time 3, you'd have division by 0 there. There's something kind of interesting about these solutions in terms of the way they behave. They have singularities as you evolve time that aren't apparent in the original differential equations. Okay, so, but this doesn't always work, right? Yeah.
Would that be scalar?
Would that be scalar?
Or vector?
I mean, it's the position vector. So I can either think of, you know, this point here as the point a comma b, right? Or I can think about it as the vector a comma b. Them's your choices. I have chose to think of it as a point here, but if this is better, fine. Yeah, I mean, it's not a meaningful distinction in here at the moment. So example 2, what if my vector field f is like, oh, I don't know, minus y x, like that, and I want to find, oh, this is fun, the integral curves to that vector field. How would I do? Can I do that? What do you guys think? You know, it's too bad we don't have a regular time, Monday, Wednesday, and Friday, when no classes happen, where we could do this sort of thing without disturbing classes. If only there was such a time set aside in our schedule. Wouldn't that be wonderful? So can you find the integral curves to this? Like, well, we'd have to solve dx dt equals to minus y, and dy dt equals to x. Right? Now they're intertwangled. They're coupled differential equations, right? We don't currently have the technology to solve that. We'll learn that in a few weeks. All right? So at the moment, we don't know. We don't yet know how to solve, right? So what do we do? The answer is we use a little trick. See, we can actually find integral curves. So at the moment, I've just showed you how to find parameterization of the integral curve, right? What if you're just content to find the Cartesian form of the integral curve, right? So let's do that. Cartesian form. We'd have dy dx, right? That's what I want to find an equation for, dy dx. How about this? I replace dy with dy over dt. And I replace dx with dx over dt, right? So basically dividing top and bottom by dt. But if we want the integral curve, dy dt should be what? It should be q, right? And dx dt should be p. So in other words, this gives us a little theorem. Integral curves to f equals to p comma q given by solving, well, by solutions to dy dx equal to q over p. And as long as the p and the q are just functions of x and y, we've got a shot at solving these, right? Like, let's try to find the integral curves to example 2 in this way. So what do we got? What are we up against here? What's that?
Never mind.
That's okay. So my q is what? My q is x. My p is minus y. Hey, we can solve this. This is, you know, like taking candy from a baby, as they say. Although, if you've ever tried to take candy from a baby while they're awake, it's not a very good saying. It's actually really difficult. Come on. So integrate both sides. Woohoo! And we get minus 1/2 y squared is 1/2 x squared plus r squared over 2, because what else would you call that constant? Oh, I know what you'd call it. You'd call it minus r squared over 2. And that gives us x squared plus y squared equals to r squared. You see, the integral curves to this vector field are circles. This vector field encircles the origin in the counterclockwise sense, actually. So like here, if we can draw 4 vectors for it, right? At 1, 0, where's the vector field go?
Undefined.
Whoa. Whoa. I think it's 0, 1, yeah? Which looks like this. And then, let's see here, what is f of minus 1, 0? 0, minus 1, right? So, like this. And then f of 0, 1, what's that? Minus 1, 0, right? Putting it in. So, like this. And then f of 0, minus 1. We get 1, 0, right? So that goes like this. This might get the video banned. I should be careful. I don't know. Hey, it happened. It just happened. I'm sorry. I can't help it. So here's the integral curve, all right? Yeah, now it's okay. All right. Yeah. Now it turns out that system of differential equations you can solve, the solutions are like sines and cosines, which are actually the parameterizations of that circle. We'll get back to that eventually, but so at the moment you can find integral curves. You simply take the ratio of the y component to the x component and solve dy dx equal to that. That gives you integral curves. And we can go back to example 1 and try this out on example 1 as well while we're at it. So like example 1, our Cartesian, if we want the Cartesian form, we'd be solving dy dx equal to what? My q is y squared, and my x component was x squared, so that's my p. And that gives me, of course, like dy over y squared equals to dx over x squared. Integrate both sides. Use a marker that actually writes. This gives us minus 1 over y is equal to minus 1 over x plus a constant. So therefore, the Cartesian equation of those curves is simply y is equal to minus 1 over c minus 1 over x, I guess, which you could rewrite differently if you wanted. I guess I could write that as, you know, x over, say, c, x over x minus cx, I suppose. And again, you can see that weird thing going on if I write this. This is just kind of fun to look at. That's x times 1 minus c. Yeah. I feel like I did something wrong there. There's just yeah. I think I should just have a 1 down there, right? Like, I'm sorry. This is not right. Multiply top and bottom by minus x. I get x. I get minus cx. But this is just 1. Yeah. So you notice that you've got division by 0. At 1 equals to cx, right? Or x equals to 1 over c. Which is a kind of weird thing if you think about it, right? Because there's nothing funny happening in the differential equation itself where there's a divergence in the solution. That's an interesting phenomenon. It's not surprising to find divergences in your solution where there's also like discontinuities or divergences in your differential equation, right? I expect that. But anyway, these are integral curves. So let me, I also was supposed to share with you the theory of differential equations, which I have neglected. There's not a lot of theory to share with you guys in this part of the material. There's like basically one main theorem, possibly two. And what the theorem says is essentially this, that if you have a very mild condition on the equation which defines the differential equation, then there's a solution that exists. And that's kind of it. Let me show you the theorem rather than writing it out, because there's also a couple pictures I wanted to show you in the notes. So let's do that. So, if this was a math major course, we might spend a couple of weeks deriving these theorems. All right? Because the proof of the theorem is actually interesting. It requires something called the contraction mapping principle. You start by defining an iterative procedure to solve the differential equation, and then you have to show that that iteration converges to a certain thing. The way that's done is with this contraction mapping principle. But that's obviously not appropriate for this course, right? We're interested in solving differential equations. It's not a proofs class. You know the deal. But it is important for you to at least see the theory. And there's also something we should talk a bit about. So, like this picture, what is this about? So this is this is very much connected to the discussion we were just having, isn't it? You know, if I'm looking for, so what this has is x prime equals to minus y and y prime equal to x. So, in other words, these little dashes are lines that have like slope defined by these values. I'm trying to put it in words here. Sorry, this is what I get for not starting at the beginning. So I'm looking for so I'm trying to explain geometrically what the this whole discussion is about, explaining geometrically what those solutions to an exact equation, how they relate to the m and the n defining the exact equation. So it's a little quirky because those curves are not tangents they're not integral curves of mn, but they end up being, I think, integral curves of either n minus m or minus nm, in a nutshell. So, like here, You know, if I looked at the vector field x comma y, these are not integral curves to x comma y. X comma y is the vector field which points, you know, like radially out from the origin. This is actually, these are what we just did, this example we just did, right? These are the integral curves to minus y comma x, which is not, you know, which is what you get if you like put a minus on that one and put, and keep that one the same and just flip them in terms of x and y. Anyway, to read the notes, the discussion's right there, all right? But this picture you're looking at is called an isocline field. What the way this works is the slope of these little dashes is given by like dy dx. So if dy dx is 1, you got like a slope 1. If you got dy dx is negative, you got like a negative slope and so forth. And you can create this picture. Here's another one. For dy dx equals to x plus y minus 6. It's kind of funky. So this is something weird happens when y is equal to like 6 minus x, right? That's going to be a place where you've got dy dx equal to 0. So you can kind of see that in here. That's that funny, very exceptional solution to this, which you can kind of see the horizontal lines here, right? There's like a horizontal tangent for the solutions that go through there. So my larger point to you is that we could make these plots and then just basically try connecting the dashes in order to solve differential equations. Like that's another way we could envision solutions to differential equations is we simply plot dy dx, like the little dashes with little slopes representative of the value of dy dx, either positive, negative, or 0, or infinite, vertical, right? And then if we connect those dashes using numerical methods, then we're looking at solutions to like this differential equation. And we can do this even when we can't like closed form solve the problem, right? If we can't solve the problem, we can still find, I like this one, direction fields. So here, this differential equation, dy dx equal to y cubed plus x squared y minus x over xy squared plus x cubed plus y minus x, has the isocline plot like this. And you see what's happening is there's this like, if you rewrite it the right way, there's an x squared plus y squared in here, and something exceptional happens on the unit circle. And what happens is like all the solutions inside the unit circle either spiral into the middle or spiral out, depending on how you want to look at it, I guess. And the solutions outside the unit circle all get dragged into it. You know, it's very cool. This can be solved using a change to polar coordinates. And I haven't typed that out, but it's in my old handwritten notes if you want to look at it. So that brings us to the theorem I was talking about. And so here's the theorem. First of all, we're talking about dy dx equals to f of xy. The question is, when can you solve that? When can you be sure you can solve it? And so here's the theorem. If this is a continuous function on a rectangle, then there is at least one solution existing at each point in the rectangle. Moreover, these solutions exist on the whole of the rectangle in the sense that they reach the edge of R. So if I got a rectangle and I have continuity of the defining function for the differential equation, if I pick a point in that rectangle, I can find a solution to the point, and I can be sure that that solution will have a domain that extends as far as the rectangle goes. Or I should say until it maxes out in the y. So it may not have, the domain might not be the whole x, but like these things are easier drawn than spoken. Here's the rectangle. I have a solution like this, right? The solution curve might, suppose the solution goes through that point. The solution might go like this. All right, that might be all I get. So, but I am guaranteed that it at least goes to the edge of the rectangle. All right. However, you notice, well, you might not notice, but nothing about a unique solution in the first theorem. There could be like tons and tons of solutions. There could be hundreds, thousands, whatever, of solutions through that one point, but every single one of them continues to the edge of the rectangle. I know that much. All right, given that continuity. So the next theorem is if we have f is continuous on the rectangle and the y derivative is non-zero. All right, then there exists a unique solution near that point. So that's pretty cool. And here's a picture of that. Well, here's a picture of when that might fail. If I have dy dx equal to y squared, well then my f of xy is y squared. If I calculate partial f partial y, I get 2y. So see, I might get into trouble I might get in trouble where y is equal to 0. I might not have a unique solution there. If I was away from where y is equal to 0, I'm guaranteed to get a unique solution through a given point, right? That's what the theorem says. And, oh, hey, we just solved that, didn't we? So this is y over 1 minus x plus c, right? That's going to be one of the possible solutions. But this also has the extraneous solution, y equals to 0. So points off the x-axis have locally unique solutions. Oh, actually, in this case, y equals 0 is also unique. But that is, so this is an example of what the theorem doesn't say. What the theorem doesn't say is that if the condition's not met, it's automatically the case that it's not unique. All right, it could be, but it might not be. I think the next example illustrates not. So here's dy dx equals 2 square root of y. And I like this one because it illustrates a certain utility in what's called p-plane. And so here partial f partial y is 1 over root y, right? That is definitely not 0 and not continuous when y is equal to 0, right? Trouble. And that's reflected in the graph down here. So like, first of all, the differential equation, dy dx equal to the square root of y, it's not even, its domain of definition is non-negative y, right? But on the edge of its domain of definition, you've got a failure of uniqueness theorem. Well, anyway, the uniqueness theorem doesn't apply there. It didn't fail. It's just, you don't have uniqueness of solutions. You have like, the y equals 0 solution intersects infinitely many solutions on the y-axis in that sense. So there's that. If you look at the first order linear ODE, which is one of our favorite problems, and you rewrite, so this makes, for the linear problem, the f of xy is q minus p y, like this. If we take the y derivative of this, what do we get? We just get minus p, all right? So as long as the defining function p of x is not equal to 0, we can expect there is a unique solution. But if p of x was equal to 0, we might have more than one solution going through a point, possibly. All right, so that's the theory in a nutshell. There's not too much to say, and then we're in the practice problems. So with that, I will let you guys have the rest of the time for the first surprise the technician. Once you're done, you can go. If you're interested in the proof of the theorem I'm talking about, I think it's on I think I put those videos on YouTube. If you're interested, email me. I can send you a link. So, thanks, guys.